Thank you very much, Matwira, for your very nice introduction. Also, Paispamo, for your introduction too. And welcome everybody who's attending our webinar today. This is the 9th in a series of webinars that have been organized by PT Multibangun Rekatama Patria. And as ever, I would like to thank very much all the hard work done by my colleagues who arrange these webinars so effectively and efficiently. I think the only difficulties they have is the fact that sometimes the internet makes life slightly difficult for us, but I think we all get used to that these days. Anyhow, so today I want to talk about something which is a very specific topic in reinforced soil technology, about load-bearing bridge abutments. And why have I chosen this topic? Well, there are many applications of reinforced soil techniques, but I think this particular one is interesting because, first of all, we're dealing with very high loads, very high risk, and serious consequences if something were to fail. So if you like, it is pushing the technology to the extreme. And I think that's why I like to talk to people about it, because it shows what you can do with these reinforced soil techniques using polymer geogrids. The talk today is not highly technical. There are a few technical bits here and there, but a lot of images and messages about the capabilities of this technique when we use it for this particular application of load-bearing bridge abutments. Exactly what I mean by that will become clearer as we go along. So as you've heard, this is the 9th in this series of geotechnical webinars organized by PT Multibangun Rekatama Patria. And we're looking at load-bearing bridge abutments. And this is the important point, that the load from the bridge deck and any live loads is carried by the polymer geogrid reinforced fill beneath it and then transmitted down into the foundations. That's the important feature. I have made this presentation a few times before. In fact, it goes back a few years in its original form in New Zealand, and I've also done this in Australia, or here in Jakarta once to the IC, and also in Malaysia. And just to let you know that our 10th webinar, we will be looking at another reinforced soil technology technique, which is the design of these structures and their performance when we have strong earthquake shaking. So that'll be our next event, which will be in November. So anyhow, back to today. Oh, sorry, before I get there, there is the outline of the webinar series that we've been doing. You can see we've now reached October. We do have 2 more to come, as I mentioned one of them, and then there will be a final one in December on a slightly different topic. I might mention that again if I have time towards the end today. So let's have a few images of these structures. We'll meet these all again later on. So here's a very nice looking bridge that you might see anywhere, but this is actually a load-bearing bridge abutment supported by reinforced soil. So is this? It happens to be a temporary bridge. Another one here, built quite some time ago. We'll also see a bit more about this one shortly. And another one here. This one is interesting because it's actually carrying a road over a railway line. This one is in Australia, Barney's Point Bridge. We'll look at that one in some detail later on. And also this interesting looking bridge in the Netherlands, which is carrying railway loading. But I think you can already see from those pictures a wide variety of possibilities when it comes to load-bearing bridge abutments using reinforced soil to support the loads. So I think by now you've realized what the main aim of this talk today, but the important point is, and I'll repeat it one more time, that we're looking at structures where the loads from the bridge deck, both live loads and dead loads, are supported by the reinforced soil mass beneath. There is no other concrete structure inside the reinforced soil, just soil and geogrid reinforcement. It's not a very new topic or not a very new application, and we'll learn a bit more about that also as we go along. As usual in my webinars, I've got these little blue boxes that pop up from time to time, which provide a bit of additional information and maybe a question or two. So really, this is aimed at civil engineers who are involved in reinforced soil projects or projects where you might want to make use of reinforced soil. And hopefully should be of interest to more experienced geotechnical engineers and geosynthetics specialists. I've just mentioned some abbreviations that will come along on the slides here and there. RSS, reinforced soil structure, RSW, reinforced soil wall, and LBBA, load-bearing bridge abutment. So you know what those mean as we come along to those particular abbreviations. It just saves me typing these things out many, many times. So here is an outline, which I think I'll briefly go through this, but some definitions and then some historical information with a few early examples and some more recent ones. Then a few brief words about design approach. In a 1-hour webinar, I can't do anything in detail on design, but we can at least look at some of the basics. And then a few words about material properties. And then perhaps the most important thing of all, we'll look at performance, particularly static performance, and a little bit about performance under shaking from an earthquake. So that's the outline today. So here is a bridge abutment. It's actually in Brunei, but in this particular case, the load from the bridge is carried by an independent concrete structure, which we cannot see. It goes through the fill, and the reinforced soil is just forming some rather nice walls underneath it. And a similar case, again, this one in the Middle East, quite a complex structure with 2 abutments. But again, those abutments are both carried by independent concrete structures, which are inside the reinforced fill. And yet another one in New Zealand. In this case, what you can see here is that the supporting structure for the bridge is in front of the reinforced soil mass, which forms the approach to that particular bridge. So let's look at this now with some pictures. So that last case was rather like this, where we have a reinforced soil structure, which is the approach structure to that bridge, and then the bridge itself independently supported in front like that. And that's one quite common arrangement. And the other one is like this, where the bridge support is actually inside the reinforced soil mass, so you can't really see it, but you can actually still use the reinforced soil wall itself to form the front of the abutment, which is nice because you can take advantage of the nice aesthetically pleasing looks of the techniques in that case. So let's have a look at what these could look like. So in this case, here is a bridge abutment under construction. And you can see in this case, the supporting concrete structure has been isolated from the fill. And so there will be no interaction between the two. That's quite common. And then the bridge abutment, of course, will be on the top of those concrete structures. So in this particular case, reinforced soil is being used to form the abutment around the structure, but it's not load bearing. It's not carrying the load of the bridge, in other words. Now, here's another option, which quite often happens. In this case, the piles are not isolated from the fill. They're simply within the fill, and the fill is still built up around the pile, and the pile itself will be supporting the bridge load when it's completed. In fact, that particular situation sometimes causes a bit of uncertainty in design. What do you do about that pile within the reinforced soil mass? It's a quite common discussion, but today we're not talking about that. We're going to be talking about something different. In fact, what I want to talk about for the rest of this presentation and webinar is reinforced fill structures like this, where they support the load from the bridge deck. This is the whole purpose of the webinar today. So a few examples. This one from the United Kingdom in around about 1990. So it's a load-bearing bridge abutment. I use that abbreviation LBBA. And in the US, if you're familiar with terminology there, this is often called a true abutment. But you can see there they are laying out Geogrid. This particular bridge will be resting on bearings, but we'll come back to that in a minute. In this case, one point to note here, it's a pretty good high quality fill. I'll talk briefly about the fill that we should be using again later on. There it is, almost completed. And completely finished in this picture. Now, this actually was a temporary bridge. One thing interesting about it, the load from those bridge girders is going straight through the reinforced fill that we just saw, but it's designed to carry very heavy loading from mining trucks. So quite an interesting particular example of this technology. So in that particular case, the cross section would look something like this. So we have the bridge girder resting on a bank seat, and the bank seat supported on the reinforced fill. So that is quite a common arrangement. And in this particular image, I'm showing the bridge supported on a bearing, which allows the bridge deck to change its length slightly due to temperature and so on. And that is one option, and perhaps most of the earlier bridges with reinforced soil abutments were built using the bearing approach. There is another option becoming much more popular now, which is the integral abutment, whereby there is no bearing, and essentially the bank seat and the bridge deck form a single unit. Just show you an example of that under construction. So here is a bridge abutment being built, and you can see there the back of the bank seat being built right behind the facing of the wall. We'll see that from the other direction in a minute. And this is an integral load-bearing bridge abutment, United Kingdom in 2015. There's the view from the front during construction. So you can see the bank seat there, which will be built up to carry the bridge girders. And there they are in position. So it's now nearing completion. It's using a modular block facing in this case. And there is another view of it. So this is actually a 28-meter span over a fairly major road in the south of England. And there it is, pretty much completed. And a final view of it in use. So I think it's a very nice example of this kind of technology in use. As I said, it seems to be becoming more and more popular these days. And one of the nice benefits with regards to the integral abutment is that the reinforced soil structure is somewhat ductile. It's able to deform a little bit, which of course you need in this case. So I think it's a very good combination using integral abutments with reinforced soil support underneath. Perhaps you'd like to look at the cross section of that particular project. So just to show you what they look like, you can see that the reinforcement is relatively long compared to the height of the structure, but that's part of the design requirement that's being followed. And that particular designation there, the granular fill type 6I, 6J, this is a UK designation, but that's a good quality fill. And you can see also that the geogrid is quite closely spaced and even closer at the top because the loads are at their highest there from the abutment seat. There'll be some backfill behind it, and then the integral abutment rests quite close to the front. This is drawn roughly to scale, bit of infill there, and we build the road on the top. So there is the complete cross section of that previous project. And what is interesting, and for those familiar with these things, are the loadings involved. So we have on top of that a 300 kilopascal dead load. That's obviously from the bridge itself, and up to 200 kilopascals live load. That of course is from the traffic. And there will be a braking load, so that there will be horizontal loads as well to be carried by the bridge abutment system. But it's a very good example of this type of technology in use. Now, question here, is this a new idea? Well, I've already answered that question, but I'm going to just answer it again. And I was lucky to go to Munich in 2018 and attend an IGS workshop from the reinforcement group. And one of the sessions was led by Professor Jorge Zornberg, who talked to us quite recently at an ENA IGS webinar. But he had a session on another one of his specialities, which is load-bearing MSE, mechanically stabilized earth abutments. And he presented information from a worldwide survey to get some idea of the use of this approach. And it turns out to be quite widespread, in some countries more than others. So for example, in US, UK, and Europe, it seems to be increasing. Not so sure it's quite so much in Asia, but maybe that's something that could change. And that's with the exception of Japan, which I'll mention briefly later on. So we learned something about the experience with this technology. So the answer to the question above is definitely no. We've already seen a temporary structure built in the UK in 1990, which is what, 31 years ago. And let's look at another one. I particularly like this structure because it just looks nice. And so what's being built there is a polymer reinforced soil block. You can see the steel bridge beam resting on top of it. There is a central pier. This one is being built in 1990 also, as was the previous one. And it's using a post and panel style of facing, which was something people tried to use in those early days because it made use of readily available components rather than specialized ones like full height panels, which we'll see later on. And this is to carry a fairly major road in the UK over a river. And it's designed to a code B378, which was a sort of precursor of BS 8006, but specifically for load-bearing bridge abutments. So that is what it looks like. There it is finished. Now, in fact, because UK people like brickwork, that original facing was actually finished with a brick look, so it looks very nice. It is brickwork, very, very attractive. And there's perhaps a rather clearer view of it that you can see there. And I thought, I've looked at these pictures many times for many years, and I thought, well, what does it look like today? Sadly, no chance to head off to the UK to check it out myself, but luckily the internet can come to our rescue, and I found this rather nice picture. There is the river, and we can see the bridge abutment there. This was about after 28 years of service. And also because of the incredible abilities of things like Google Maps, I could actually look at the top of the bridge. So you can see there you can see the steel railing on either side, and you can also see the expansion joint just behind that truck. And it's rather nice that we have a couple of heavy vehicles crossing the bridge at the moment of that particular image. So yes, this particular structure is still serving its purpose very adequately 30 years on. Another one a bit younger. This one I think is built in about the year 2000. It has an extra feature which is quite interesting. This is the west of England, and parts of the west of England have some quite soft soils. So in this case, this abutment is supported on piles, which you can see there in the diagram. And then what's called a load transfer platform is placed over the piles to spread the load from the abutment above into the piles. So we're seeing two geosynthetic technologies being used there at the same time, but it permits the load to be spread nicely down into the load-bearing layers further down. This is crossing a railway, as you can see from the picture there. There's a train going by. And again, they're using modular blocks, and at this stage, it doesn't look particularly attractive. But again, with this desire to have things covered in bricks, it was later covered in brickwork. And that was the final look of the structure. And a general view of this one, we can see it here. It's a very elegant looking bridge. And again, I thought, well, what does it look like today? And if we go again and make good use of Google Maps, we can see it there carrying on doing its function extremely well, in this case, after about 20 years or so. So two examples of bridges. They were both using bearings. They were not integral, but just showing you some of these early examples. So let's talk briefly about design. Is there guidance available for load-bearing bridge abutments constructed from reinforced soil? And the answer is most definitely yes. The obvious one you would go to if you were working in the UK, and certainly some of those examples we saw were in the UK, would be BS 8006. And Section 6 provides information on how to carry out design for these structures. It was first published in 1995, and already it had the advice back in those days as well. So you can see that's 26 years ago. And it covers the ultimate limit state and serviceability, which is important, and I'll mention that again briefly as we go along. But there's no earthquake loading. So if you're designing for earthquake loading, like you would be in many parts of Indonesia, then BS 8006 doesn't give you advice on that. So you need to be going elsewhere. Just to show you, this is a piece of software that we've developed over the years, which is for design of reinforced soil retaining walls in this particular case. But what we can also do in this case is to add a bank seat. So we can add all the required dimensions to get the right shape of the concrete structure. Plus, of course, the imposed loads you can see there towards the top left-hand part of that window, you can see the vertical and horizontal loads that have to be added. Today, we're not going to talk about the details of this, but it's just the principles. You can then add that to the system of loading. Also, we carry out a post-construction strain check on the reinforcement, and we limit that post-construction strain to 0.5%, which we'll see again briefly in a minute. Then the program does a check of the stability of the bank seat itself. And it looks a rather hair-raising view, that one, with lots and lots of numbers and so forth. But it's what it's doing. It's taking 6 different load cases. Both we have the temporary case where we don't have the bridge in place, and then of course we have the long-term case with the bridge in place, and they both have to be looked at individually. And then we calculate the loads from the bank seat, which are applied to the top of the reinforced soil structure. So that's the cross-section we would then see, and then that can be analyzed, taking into account those additional loads from the bridge applied into the reinforced soil mass. Now, this is using the BS 8006 tie-back wedge method, and in this one, you can see we've achieved a satisfactory layout of Geogrid. And then we can do this post-construction strain check. So what you're seeing there, in this particular window, the little gray diagrams on the left with the colored bits in them, those are an assessment of the distribution of strain, post-construction strain, along each piece of Geogrid for the long term. And then we can take an average value, and the profile on the right-hand side where it says average strain, if you can read that, and you can see that the limit of 0.5 is given there. So as long as you remain inside the green zone, then your post-construction strain prediction is within the requirement of BS 8006. We're going to come to that again briefly in a second to explain how that is actually working. Now, there we have our design, it's satisfactory, but maybe in Indonesia, we want to look at the case of earthquake loading. So we have some help. The AASHTO LRFD bridge design specifications, that's no longer the latest one, that's 2012, you can see there. There are now much more recent ones. But this provides guidance for load-bearing bridge abutment design using limit state methods. It covers ultimate limit state and earthquake loading. And there is, if you like, an accompanying document published by FHWA with that particular reference there in HI 10, 024 and 025. And this is nice because this is also based on limit state, and it's using the LRFD approach, therefore, but it has a very nice detailed worked example in Appendix E5. So if you want to understand much more about the calculation procedure, you can go and look inside that particular document. Appendix E5 will tell you a lot. Sadly, in a way, it doesn't, the worked example doesn't include earthquake loading, but you'd have to see how that works by looking at the rest of the guide. So what I've done now, I've taken that same case and I've switched it over to that particular method. So if you can read there halfway down the panel on the left, LRFD AASHTO 2010. And you can see that we have lots of messages that we have inadequate behavior of this abutment. That's mainly coming from connection issues, but that's a bit of a weakness of that particular technique, the tie-back wedge. However, this means if we wish, we can analyze it using that technique. But what we can also do is switch over to a 2-part wedge method. And this is something I talked about actually in our previous MRP webinar, the benefits of using a 2-part wedge approach. And that's what's going on here. So all of those green lines you can see in the cross section there are wedges that have been analyzed, taking into account the bank seat loading and giving a satisfactory result, and much more efficiently than tie-back wedge. And there is the result of an internal calculation. And you can see here in this, we have two different loads. Z is the applied load, R is a resisting load for any particular wedge. And you've just got to make sure that our CDR, that's capacity demand ratio, the ratio of the two is greater than 1. And you can see in this particular case, it is. And that can be done for the static case. And if you can also see down there, the dynamic and with both the vertical acceleration up and down. That's a topic I'm going to talk about more in the next webinar when I talk about reinforced soil design, this issue of the vertical component of acceleration and why you might want to take it into account. So that's something to talk about next month. And there we have a satisfactory design. Other documents, yes, there are some more around. This particular one, an NCHRP coming from TRB. This is quite some time ago, 2006 it was published. But there is a more recent one from FHWA. This one was published in 2018, and this one includes earthquake loading. It's quite a comprehensive guide, and you can see some nice pictures there of bridges which are using what is called the true abutment, or the load-bearing bridge abutment to carry the bridge deck across, in this case, a river. Now, moving on a little bit, a few comments on material properties. This is a construction we saw earlier on, but if you're going to consider reinforced soil techniques for carrying bridge loads, then your reinforced fill must be good. You need to use basically a well-graded granular fill, which is what's going on here. You can see this would be a sandy gravel. And you'll see also later on in some of the examples I show you the use of sand fills. Of course, a good quality sand would also be extremely good. This is almost certainly a case where you'd want to avoid clay fills, not because you couldn't design for them, but I think more because the deformations may be a bit difficult to control in service, especially the vertical deformations. So this is definitely a case where it would be wise to avoid the clay fills or the Tanamera fills, I think, for load-bearing bridge abutments. Just a few words about the polymer geogrids. We can see some geogrids laid out here behind a panel wall. It's not actually a bridge abutment, but just to remind us what these materials can look like. These are HDP geogrids. And in order to carry out our designs, we need strength values for ultimate limit state, that's to say long-term failure, serviceability limit state, that's to say controlling deformations, and also the seismic case. And I'm just going to add a few words about these. So here is a kind of well-known formula that you can see in the middle of the slide there, which gives us the design strength, in this case for the ultimate limit state, in terms of a number of factors. It's quite a well-known equation, that. And if you look at it, you have TCR on the top, which is the long-term creep rupture strength. And then along the bottom, you have a number of reduction factors to do with things like installation damage and environmental effects, weathering and chemical effects, and so on. Now, as you see it there, this is defined for the ultimate limit state, in other words, failure or rupture of the geogrid. But when it comes to load-bearing bridge abutment design, we also want to have a second definition, which is for the serviceability limit state, which are called SLS for short there, inside the red circle at the top, near the top, in the middle of the slide. And we've now slightly changed because we're now using a thing called TCS. And that's the load which is going to limit the post-construction strain to a certain value. And that's what I want to talk about briefly. So to find out this particular piece of information, we need to carry out what are called creep tests, where we hang up specimens of the geogrid in a creep laboratory with weights on the bottom, and we measure their strain against time. I did talk about this briefly in the previous webinar as well. But today I want to concentrate only on one thing, and that's deriving what we call isochronous curves. So from the creep data, we can derive load strain curves. Now, load strain curves are things that people like to see when it comes to, say, a tensile reinforcement. People understand this very, very nicely. It's that very, very important relationship between load and strain. And we can derive it in this case for a duration of 1 month of loading. And that's what we see at the moment on that graph. We can also derive a second line, in this case for a 120-year duration. Now you might say, well, how can you possibly do that? We haven't been doing creep tests for 120 years. Well, we can use high temperature testing to help us do that. Again, that's quite a long discussion. Please accept my word for it for the time being, but we can do that by careful interpretation of creep testing using high temperature data. So we now have two isochronous curves, one for 1 month and the other one is for 120 years. And then what BS 8006 requires is that the post-construction strain should be limited to 1% during working life or post-construction. Now, it is assumed that post-construction is from about a month to the end of design life. In other words, between those two curves that you can see. So if you look at the distance between the curves and you find the point where it's 1%, so the strain axis is 1% along the, is in percent along the bottom, then in this particular case, TCS is about 20.6% of, in this case, the tensile strength of the material. You can see TCR also on this diagram. I've added that as well, so you can see how they compare. Now that's to limit post-construction strain to 1% for retaining walls. But when it comes to load-bearing bridge abutments, the BS 8006 recommendation is that you limit post-construction strain to 0.5%. And so you can now see in this case, it's a lower value, it's 13.1% of the tensile strength. And when earlier on we saw that little window pop up with the 0.5% in it, that's what it was limiting when we set that within the design procedure. Perhaps just worth mentioning that when you carry out design of load-bearing bridge abutments with reinforced soil techniques, then sometimes because of this 0.5% requirement, it's quite often that the SLS check could be more critical than ultimate limit state. And in fact, in the early days, say the BE 378 document, that design procedure was based on serviceability mainly. Just leaving strength behind and going to durability, just a few words. Again, I covered this in quite some detail in the last webinar, in MRP 8 webinar, but we need to be very careful about this. We need to check that we have adequate durability, and that's normally in terms of things like weathering. Well, you're not going to expose the geogrid for long in a load-bearing bridge abutment, so that's not going to be too much of a problem. But things like microbiological degradation, oxidation, and the effect of acids and alkalis. And they need to be investigated using both screening tests, which are quick tests, but to get the real long-term predictions, we need to carry out a lifetime exposure tests. So this is a really important thing, especially because durability becomes even more important in hotter climates. Generally, polymers will be affected more rapidly under higher temperatures when it comes to degradation. So we have to be extra careful when it comes to the climates like we have here in Indonesia, where it's generally hotter and wetter. So please take that into account when you think about these things. So let's leave those material properties behind and now look at some measured static performance. And let's start with one of the very early ones. It's interesting, certainly in the UK, this was built in Stirling in Scotland. It's just a pedestrian underpass. It's not a very huge span, but it is carrying a road load. The structure on top is a road, so it's carrying normal traffic loading up to heavy trucks. And this one was dating back 35 years now, so quite a long time ago. And because it was a very early structure, a lot of attention was paid to it, and there is quite a comprehensive it used to be called TRRL, it's now called TRL, Report 128, which tells you all about the construction and monitoring of this particular structure. There's a cross section of it, so it's using this panel facing, and the geogrid is connected to the panel, This is a detail we'll see again shortly, so I'll give you a bit more detail about that shortly. And also, in this particular case, there were some compressible soils beneath the structure. So they used a cellular mattress, which today we call it stratum, to help support the abutment and carry or spread the loads into the softer soils underneath. So there, it was a simple little structure by today's standards, but a very early one, and obviously lessons were learned from that. And when it comes to the monitoring, it was found that the total deformation at the top of the panel was less than 20 millimeters, and it rapidly stabilized. If you want to see this in more detail, you'll have to get hold of that report or ask me for a copy of it, but you'll find a lot of information in there. The vertical settlement actually was bigger than the horizontal movement, but because of the slightly compressible subsoils, they got up to about 58 millimeters of vertical settlement, which also reduced with time. And when it came to the geogrid itself, the maximum increase in strain during the service period was about 0.7%, with a mean value of about 0.3. And I've got a feeling that this data was part of the contribution to those early limits that are still published today in BS 8006 about a mean strain limit of 0.5% for load-bearing bridge abutments. And there we are. If we go to Google Maps again and make use of the incredible abilities of that technology, there is a view on top of the bridge. You can see the shape of the concrete edge of the bridge there, the parapet, and you can just about make out the construction joints on the left and right of that picture. So still happily doing its service as it should do 35 years later. Only a little bridge, wasn't it? But we'll look at some bigger ones in a minute. And here is a bigger one straight away. It's one that I saw from day one pretty much. Barney's Point Bridge, which is built over the Tweed River, which separates Queensland from New South Wales on the east side of Australia. This one was built in 1993, so this is getting quite old now as well, 28 years or so. And this one is using a sand fill with an HTP geogrid. And it's using a modular block facing, which you can see very clearly there. And also in the distance, you can see the old bridge in that particular photograph. And also because, again, it was early use of this technology in Australia, it was quite carefully instrumented. So, for example, one thing that we used were these load bolts to try and measure the load in the geogrid. Now, there was one slight issue with that approach there because the load bolt system is so stiff, it was attracting too much load. So, in fact, they overread the load in the geogrid. So, measuring load in geogrid is not easy. Rather simpler is measuring strain, and this was done with strain gauges of this type. Again, these were on the top or bottom of the geogrid, so they work reasonably well, and we did get some quite good data on strain measurements. But there we have a nice view of it. You can see approaching completion, not in service yet. But perhaps some of the most useful bits of instrumentation came from two things. First of all, there were targets on the facing that allowed us to measure the forward movement of the structure. And to be honest, if you're looking at instrumentation of these structures, that's one of the simplest and cheapest things to do. Simply put some targets on the face and use accurate surveying techniques to measure their location and their change in location. But we also had inclinometers, which are positioned here. That's I1. And on the third berm up, you can see there's a tiered, it's like a series of steps, the shape of the structure. And on the third tier, they positioned I2. And we're going to have a look at this information in the next slide or two. So there we have a nice cross-section of the structure. So you can see there the tiered shape, the series of steps that form the facing. Quite a high load. The typical loading from the bridge in the order of, for the design anyhow, was in the order of 400 kilonewtons per meter along the abutment. So that's quite a high load. Overall height about 12 meters from the original ground level up to the road. And you can see the position there of I1 and I2. Now, one nice thing about inclinometers is as long as they don't get blocked, or too distorted, they will last for a long time. Many instruments like strain gauges and things, they are unlikely to keep going for 30 years. But inclinometers, generally not bad. So we have some data here, and I'll talk a bit more about the shape of the graph as we go along, but you can see there are 3 traces. So I've superimposed that graph on the inclinometer, so it matches the ground conditions. So if you look at the ground conditions, we have some sands. There is then a sandy clay layer, and then there's an upper sand, the sort of light green color, which may or may not have been a fill. And then obviously on top of that is the fill of the structure. But what you can see from that diagram, it's very clear that the forward movement is mainly coming within that upper sand layer, which is interesting. I haven't explained to you the colors of the lines yet. That comes next, because let's add I1. I1 is at the toe, and you can see we have a similar kind of extra amount of deformation in the upper sand layer. But also now you can see the description of the lines. So they're in terms of the date. And if you can read the dates there, you can see the blue line in 1994 was about 9 months into operation. So these are all post-construction. And then the green one was a little bit later, 17 months after operation. But the red one is 20 years later. Now, 20-year-old data in structures like this is incredibly good to get. You've realized by now we're actually up to about 28 years now. We don't have anything more recent than that at the moment, but I believe it could still be measured. However, there we are. That's what the performance looks like. Now, you might say, "Oh dear, this is a bit of a shame. The structures move forwards because of the foundation." But is it actually that serious? So let's have a look. So if we think about that piece of Geogrid, which I've just put into a sort of a bluish color, then if that particular length there at the point of the inclinometer is about 10 meters of Geogrid. If we assume that the buried end doesn't move, then that 50 millimeter extension at that point, let's say from the red line, is a mean strain of about 0.5%, very close to the target given in BS 8006. However, in fact, the majority of that deformation has come from the foundation soil. So if I perhaps do something which is perhaps not a rigorous thing to do, but if I remove the effect of the foundation soils like this, and I assume that we only look at the movement within the reinforced soil block, then you can see that over that post-construction time period, the deformations are very small. So that's assuming zero displacement of the foundation. So if I go to my piece of Geogrid of 10 meters length, and I now look at the mean strain, within the reinforced soil mass, it could be as low as 0.1%. So you can see that the performance of the structure is very much in line with the normal design requirements for such a load-bearing bridge abutment. So it's a very wonderful case study, is Barney's Point Bridge. And we're going to have a look at a couple more, though. I'd like to look at a couple more of these before we come to a conclusion today. Another one built more recently, Founders Meadows, built in Colorado. There are 2 lengthy research reports, and if you can read the names on those documents, you'll see again Professor Jorge Zornberg's name there. He was quite heavily involved in this. But this again was a load-bearing bridge abutment, heavily instrumented, carefully monitored, and all I'm going to show you is a few of the pages from this, because if you want to study this in detail, I suggest you get hold of these reports, and there's a lot of information in them. So here we see on the left a picture of the bridge itself. You can see the bridge girder there resting on top of the load-bearing bridge abutment, and then that diagram, which I'm sure you can't read, but those lines are showing you the forward movement of the wall, and I think that scale at the bottom is only a matter of a few millimeters, so very small movements. And then there's a cross-section through the structure, and the diagram on the right-hand side is the strain in the Geogrid during construction, And again, those strain values, if you can read them, are very, very small indeed. Anyhow, this is something to study. If you really want to learn a lot more about that particular structure, those reports are readily available. That was Founders Meadows. So now let's move to a bit more experience, because when I was first preparing the material for this presentation a few years ago, I contacted my colleagues around the world and I said, look, I'm doing this work, and certainly that previous one obviously came from colleagues in the US. I said, have you got any interesting information on load-bearing bridge abutments that I could use to help create this presentation? And good colleague of mine, Theo in Netherlands, said, yeah, we got a few. And he sent me this incredibly good information. And this was one of them. I'm not going to try to show all of them to you today, but this one is particularly interesting. And what you can see there is a railway line, of course, in the Netherlands. And they want to build a new section of line, which requires a bridge abutment inside that yellow area there. So this is what the structure. So this is what the structure is going to look like. So the blue line, which you can see in the plan view, is the reinforced soil retaining wall. The bridge abutment, you can see it clearly marked there towards the right-hand end, and it's supported on the fill, which is a sand. You'll see shortly. And the view we had just now was viewing in from the right-hand lower corner when we looked at it in that aerial view. So let's have a look at this particular structure and the details of it. It uses a technique which is particularly popular in the Netherlands, which is full height panels. It's worth talking briefly about these. We've seen a lot of modular block structures so far, which are small concrete units. Clearly, a full height panel is a large piece of concrete. So things like handling become something of much greater importance because they weigh several tons. But one of the benefits of them is that because they're full height, you can come along and put them all up very quickly and with your crane, and the crane is obviously an expensive piece of equipment. And having got them all up, you prop them and they are then going to be all put up in one go. So then the crane is finished. Anyhow, there are pros and cons with all of these techniques, but let's have a look at the results of doing this one. So what happens here after propping up the panels, which you can see in the background, and the one lying on its side in the foreground, is those little bits of geogrid will be connected to the main pieces of geogrid using a connector called a bodkin, and then that will form the full reinforced soil structure when they are compacted into the fill. You can see here that they're being propped. So that's the front nose of this structure, which is going to carry the bridge or the bridge abutment itself. And here we have a view inside that section of the structure. We can see the panels there and the placement of the sand fill. This is using a sand fill. The Netherlands, for those who know the Netherlands, has a lot of sand. So most of these things are going to be built with sand fill. That's the view now from the outside. The fill has reached almost the full height. And one thing interesting here, that because of the parts of those panels were propped on the inside, so they were able to actually keep the rail track running nearby, which is quite a nice advantage of the technique. But we now come to the moment of placing the bridge girders. And when I first saw this, I was certainly amazed. So they're placing the bridge girders here. You can see at nighttime occupation of the railway using a couple of cranes. And the span is 53 meters, which is a long way. And I think this must be one of the longest spanned bridges supported on reinforced soil load-bearing bridge abutments, as far as I'm aware anyhow. And there you can see the ends of the girders resting on the bank seat foundation itself. So below there is just sand and geogrid. And because it was such an important structure and there's so much interest, some simple targets were fixed on the facing panels at a number of locations to measure the movements. So you can see what they look like, and so they can be checked by surveying techniques. So you can see the little white marks. So if we look at B2, I'll need to explain it a little bit. So the graph is the height in the vertical direction versus the movement. 0 is in the middle of the horizontal axis. And then the next division, if you can't read it, is 20 millimeters. So because this is a panel, you can measure it from day one before you even place any fill. So the green position is when they first put the panel up, and most of that forward movement is coming as you place the fill. You can also see there's a bit of a jump in movement roughly halfway through there, but that's partly because at some stage they drove some piles into the sand fill just behind the reinforced soil structure, and that also did cause a little bit of movement. But anyhow, the thing performed extremely well, and there's a lot of information from the monitoring. So here it is now in ready for use. You can see the rail track going up this particular slope, very gentle slope. The bridge was finished off with this rather interesting look to it, and here it is about to take the load from a train. So I think for me, when I first ran through these pictures, I was quite amazed. So that's a 53-meter span carrying railway loading, supported on a reinforced soil structure. Really impressive. Another one, perhaps not so grand, but it looks more like a regular bridge. In fact, it looks very much like the one I showed you earlier on, because it's similar. A similar kind of span built in Kent in the UK. Also, these are integral abutments built in 2016-17. But there was some monitoring placed in conjunction with these abutments, and they placed some tilt meters to give some indication of the ongoing movements that were taking place post-construction. And these diagrams don't tell you a great deal, but they're very early on in the monitoring, and it's time in the horizontal axis and tilt in degrees in the vertical axis. And you can see after the initial section, the tilt remains pretty much constant. So we're hoping to like to get some more information. You can see that's going back to 2017. So we'd like to get that more up to date. There was also measurement of the gap between the bank seat and the wall at the top, which is the top diagram is the gap in millimeters. If you can read the numbers, they're very small amounts. So you can see that this gap did slightly change against time, but the lower diagram is actually the measured temperature. So the majority of that movement you can see is related very much to the change in temperature that's going on as well. So important to measure all of these variables when we're looking at performance of these sorts of structures. Now, last thing is about performance under seismic loading. When it comes to bridge abutments, the reinforced soil technique, if you're expecting strong earthquake shaking, actually makes a great deal of sense, because you have a very ductile structure, something I'll talk about in a bit more detail next month. But has it been tested? Have any of these abutments been shaken strongly by earthquakes? Well, there probably have been, certainly in Japan. But this is a test being carried out. So UCSD is University of California in San Diego. They have a number of shaking table bits of equipment, large scale ones. And in this particular case, they've built a half-scale load-bearing bridge abutment. So what you can see in the picture there, well, it's labeled for you very nicely. You have the shaking table supporting the reinforced soil abutment, which has got a blockwork finish on the left side. Then the actual bridge or the bank seat itself, you can see the concrete structure there, and very clearly labeled is the bridge deck. And you can see some loading, those steel items on the top to provide some load. And then the support wall on the right-hand side, that slides backwards and forwards. That's not anchored anyway. That moves by itself. It's not anchored. So the next part of this is a little video, and I think I need to just get it to go for you. So there should be some sound, I think. So we wait for it to happen. There we go. It starts to shake it. So there we are. So what we saw there was the modeling of an abutment, and what is normally done. This would have been shaken many times, generally with increasing amounts of acceleration. And what is normally done is that real earthquake records are used. So let me just show you in terms of the outward movement and the residual movement, what it looks like from two of these results. Sorry, I don't want to show that to you again. Stop that. Here we are. So this is the lateral facing displacement against the height from the base. Because it's a model, because it's half scale, it's only 2 meters high. And what you see there, that red line shows you the maximum. If you remember how it was shaking around and it sort of it lurched forwards, that would be the maximum outward movement up to about 4 millimeters. And then when it stopped shaking, it ended up here about 1 millimeter from where it started. So this of course is a very nice performance, but you're seeing there very clearly the ductility, how the ability to deform a little bit, but to retain function is allowing the structure to survive a fairly strong earthquake shake. This was the Imperial Valley earthquake record. And another one here, this is the Maule earthquake. So again, that shouldn't be labeled residual. That's the maximum outward movement. And then it comes back to that. Sorry, those labels are the wrong way around. I will correct those before we post the slides. So it ends up, it went out about 5 millimeters at the maximum outward movement. And then when it settled down, it was about a 1 millimeter outward displacement compared to where it started. So very nice information on how these structures perform. So that brings me to the end almost. But just a few comments that these structures have been in use for over 30 years, as you've seen, well over 30 years, in fact. And we have examples using bearings as well as integral abutments, although these days the integral abutment seems to be getting more popular, less maintenance. There are well-established design methods available, and we can look carefully at polymer geogrids and make sure that we have adequate long-term behavior and durability and so forth checked by testing. We can see from measured static performance that post-construction deformation is generally in line with design targets, which is, of course, what we want. And we can also see that we have this excellent ductility when it comes to seismic shaking. One thing just to tell you about, and this is something maybe that ENA IGS might try and arrange next year. Professor Fumio Tatsuoka, a name I'm sure many of you have heard, he has wonderful information about the performance of reinforced soil structures, including load-bearing bridge abutments, used to build the high-speed railway systems in Japan, where obviously the seismic side of design there is extremely important. Incredible information. You can certainly find the published versions of his material in many places, but maybe that's something we'll try and arrange through the Indonesian chapter of IGS next year. But before I finish, a final word from the Netherlands, because my colleague Theo again sent me some wonderful information, but this is like a bit of a story of a structure. So what are we going to look at? We're going to see a drone video, because that's what we like to look at these days, at these structures. And we're going to look at a structure which has got 3 bridges and therefore 6 abutments. And the best thing to do is to get on and start flying. So off we go. So we fly along this structure. It is at this stage nearing completion. The road hasn't been built yet, of course. And we are now approaching the first bridge. And you can see how it's clearly a sand fill, because this is Netherlands again. Right, we stop there. Let's get off the plane for a minute and have a look and see what's going on. So again, we're using these full height panels with a very nice looking finish on them there. They're propped on the outside in this case. And then on the inside, we have the short tails of Geogrid, which will be connected to the main reinforcement to provide the reinforcement effect. And if we look at the cross section, then the cross section of the bridge looks like this. And you can see how the bank seat is being carried on the reinforced soil structure itself. So this is very much the type of structure we've been talking about. In this case, it's using a bridge bearing. It's not an integral bridge. Then we carry on our flight. We keep flying further down the structure. The walls are getting higher and higher as we go along it. You can probably guess that from the view on the side. And then we start to approach the main bridge, which is over a canal. And as we approach this one, we begin to see it's actually going to be quite a big span. And we have here a view of this next bridge. Okay, so we now stop and we get off the aeroplane again. Now, this is actually quite a big span. So these abutments are not reinforced soil abutments. There is an independent concrete structure supporting the bridge deck. And you can see it very nicely there. You can see it is quite a long span. I'm not sure what it was, but it's quite long. And another nice view of it there. But there's an interesting detail here, which is worth having a look at. So if we look at what's happening underneath the bridge here, and I'm afraid the drawing's in the other direction, but we have a cross section here. What you see on the right-hand side, the red bit, that's the foundation for the to carry the bridge deck through a concrete structure, which goes upwards, of course, and it's on piles. Much of Netherlands has soft soil, so it's resting on piles. But because they then are concerned about the effect of settlement on the soil-supported structure behind the pile-supported abutment, they use a very clever transition technique where they use piles of reducing length as you come back from the pile-supported abutment until the length of the pile becomes almost nothing. In fact, it becomes zero. And on top of that, they put a load transfer platform, and then they build a structure on top of that. So the purpose of that detail is to reduce the effects of differential settlement behind the piled abutment. So there's another interesting use of geosynthetic technology, because the LTP incorporates geosynthetics. Anyhow, let's carry on flying down the structure a bit more. Off we go. Now you can see there, if we look down now, you can see they're delivering a panel there. They have a special frame there which lifts it up, and then the crane will put it into position. Then we kick, you can see this part of the structure is an early stage of construction. And then we reach the third bridge. And here is the bridge number 3. And then I think we're going to stop and we get off the plane again. Now, this is also a bridge where the load of the bridge deck is carried by the reinforced soil itself. And interesting point here is that we have a very sharp a return there. In other words, we have a very difficult geometry where we have an oblique direction of the road going underneath the bridge. So to sort this one out, we have some additional detailing to look at. So it's a very common question. What do you do when you have this situation? So if you look inside, you can see the sharp corner inside. So what they're doing there, because you can't extend the geogrid the correct length, they use concrete in the far corner. And then they also used cement stabilization of the sand for coming further back. So they had some details to help deal with that issue. But the load of the bridge deck is still carried on the reinforced soil, which you can see there. And having done that, we then carry on flying for a short way further on, I think just a short distance, as we head down to the far end of the structure. So I thought that was rather interesting. A lot of interesting features in that little flyover. 2 types of support of the bridges and some interesting techniques being used. So I would like to thank a number of colleagues, apart from Theo in the Netherlands, also Mitchell, Andrew, Willie, and Gordon in New Zealand for helping me to provide information towards this presentation over the years. As I said, it's not a newly created presentation, although some of the material is new for today, particularly that last flyover of that particular structure. Just to remind you again that in November, I want to talk a little bit about the design and performance of reinforced soil structures to resist strong earthquakes, which is slightly linked to today's topic as well. And that brings me to an end. So I